Hey, it's Aaron with ipXchange with another IP experience, this time part 2 of our series with Lotus Microsystems. So in part 1, I sat down with Hans, the CEO, and we discussed the general concept of silicon power interposers or power silicon interposers and how this can drastically improve the thermal performance in power electronics designs. But today I'm here talking with Ahmed, and we're going to really dig deep into what's so innovative about this device and technology. So Ahmed, first of all, thank you so much for joining us. And if you could just introduce a little bit of how you got there, then I'll start asking some questions about these silicon interposers.
Yeah, sure. Thanks a lot, Eamon. It's a pleasure to be here. And I can just introduce myself briefly. My name is Ahmed. I'm one of 3 founders of Lotus Microsystems. Lotus is originally a spin out of the Technical University of Denmark. And the 3 of us were doing our PhDs in the university with different flares into power electronics, integrated circuit design, and nanofabrication. We started the company in 2020. We had some IP existing at the time, and we used that basically as the main IP asset that we started. Of course, we came a long way from there. And yeah, I think it's 4 years almost for us right now. And in the company, I am head of product, so I'm overlooking a lot of the things towards the market side, while the other guys are mainly involved in the product development as well as supply chain partnerships. We're a fabless company, so supply chain establishment and is a big part of what we do. And yeah, I'm happy to share more information about the technology and what we do today here with you.
Nice. So I think the first thing to do is to just define what a silicon interposer is, and then because I hear it being used in when people talk about logic chipsets, but this is for power electronics. So how did you transfer the technology, and what did you have to change about it?
That's a great question. I think it's the right one to start with. So yeah, silicon interposers are used as substrates in co-packaging of logic chiplets. The key example for that is you have like processing elements like a GPU chip or so, and then you have the memory chips like HBM memory modules, and then you need to bring them as close as possible on a substrate, and you need to design that substrate to carry a lot of like high bandwidth signal between these different chiplets. So what you're looking for is shorter traces, and also the density of these interconnects has to be very high. And this is where silicon can come as a substrate that can support that because you use photolithography to pattern interconnects on silicon, and then you can reach sizes and feature dimensions that are much more accurate and higher density than what you can achieve on other kinds of substrates. So what we did basically is to take that substrate technology and then reconfigure it and use it for power applications. In that case, we don't carry signals, which are just like low current, like information, and it's low voltage. It's normally like sub 1 volt levels of voltages for these signals. We need to carry higher currents across the substrate, and we need to also withstand higher voltage. And this is where the design of the silicon substrate for such application has to be done using specific processes, and we have a proprietary technology for that in order to be able to use it in high voltage applications. So you can use it for power conversion from, let's say, your bus voltage, or for point of load applications, and step down that voltage to the supply voltages you need for the logic chips and so on.
Cool. So just to clarify, are these silicon interposers the type of things that you would see inside, say, an MCU connecting the core to the memory units that are built in? Is that the type of thing we're talking about?
Yeah, high performance computing generally relies on modules like AI compute modules that are based on such co-packaging. And
Okay.
the key reason for that is you need to, like, as a way to get around the limitations on technology scaling right now, instead of trying to package as much transistors into a single monolithic chip, then you would rather design every part of the system using the most relevant technology for that, so they don't have to be on the same CMOS node, and then
Mm.
you bring them together and co-package them on the substrate.
And I guess if they're handling higher currents, are the silicon interposers for power generally larger, or are they still kind of at that logic size level?
Well, it really depends. So
Okay.
when you talk about it as a technology, then it's really like a platform, and it has to do with the exact application and the size and the power density you're looking for. But what's different about the silicon interposer for power is you need to have much higher copper content in that silicon compared to
Oh,
the
okay, yeah.
content of copper you have on the typical use case. So we're talking about thicker copper traces, higher density through silicon vias that can carry the current across the substrate. The via technology itself, in terms of the mechanical design, the dimension, the filling material, the insulation materials with that, has to be designed with power in mind. You need to also be able to like withstand higher voltages across the substrate without any leakage, in
Mm.
order not to eat up your efficiency gains by having other like kind of like leakage and power escapes through the substrate itself.
So I talked to Hans a bit about the idea of Lotus Microsystems kind of being a packaging technology as well as a power technology. We were talking about the kind of power modules, or actually just general modules you get that are co-packaged things on an FR4 board, for example. What's the key benefit of co-packaging at the silicon substrate level rather than on kind of a traditional FR4 type module?
So that's a really good question. So let me start by saying like power modules in general
Mm.
are uh, a kind of a product where you need to co-package the different parts of a power converter. So in a power converter, you have some active components like the chip itself, the power management IC. Inside of that, there is specific blocks. So you have the power devices, the switches, you have the gate driver,
Mm-hmm.
and you have the control circuit. Sometimes these are a single chip, and sometimes they are separate chips, especially if you use other technologies for power devices than MOSFETs. Then in that
Also,
case,
like
they
if
are
you're having
not
to put in GAN
monolithic.
or something like that.
Exactly. That's
Okay.
again is a perfect example of that. And then you have passive components. You have inductors and capacitors. And this is because the most common topology used for conversion, high power converter, is based on switch mode power supplies. And
Mm-hmm.
in that case, you have a switching network that switches a passive circuit in order to be able to shape the power and process it and deliver it to the load. And there are two families of that. There's the switched inductor converters, switch capacitors converters, and then there are some hybrid families that combine both of these worlds. And in a power module, you end up co-packaging the active components or the active circuit together with the passives in a single package. And the typical substrate technologies for that, because then when you end up, instead of direct assembly of the chip and the inductor on your platform PCB, you're going to package them on some substrate first, and then that substrate is going to be assembled as an SMD component, like together
Okay.
with
Yeah,
the
yeah.
with the molded assembly of the components on it on the application platform. And that has advantages in terms of the um, less parasitics you get from the package, better EMI performance, smaller size, and also some ways to deal with the thermal performance of the power converter to design using the right substrate. And the typical technologies for that kind of power modules is based on two kinds of a substrate. One is a lead frame
Okay.
substrate, which is like a copper frame that the components get assembled on, and then it's over molded with an epoxy molding compound or the similar. And the other one is an FR4 substrate, or what we call a laminate substrate, and that's based on the same technology for PCB. Silicon as a substrate for power modules is basically what Lotus is about, how to bring silicon based on a silicon interposer technology to be used as a substrate for power modules. And comparing to the other technologies that of existing substrate technologies, there are many advantages of using silicon as a substrate material. So first, you have silicon is a high thermal conductivity material compared to many of the variants used as dielectrics and the other substrates. So the thermal conductivity of silicon is up to 150 watt per meter Kelvin, and that can ensure that's about effectively 150 times if we compare it to the FR4 material used in laminate substrates, for example. So that can, because when we talk power, we talk also thermal, especially when we want to increase the power density and we want to get more watts per millimeter squared of a power module that's going to consume some space on your like real estate on your application platform. So heat then becomes a key bottleneck if not taken into consideration in the mechanical design of the package as well. And then silicon offers lower thermal resistance in the substrate to take the heat out to the application board. And then you're able to deal with that heat from the application board by other means, like by connection to a heat sink or having proper like copper like content in nearby ground planes or similar. And then the other key thing about silicon is that you have high integration capabilities in silicon, because silicon is the same material is used for the active circuits, if we're talking about like MOSFETs and control circuit and similar. So it allows you also to integrate something like one or more of the power converter components in the substrate itself by using different means. So that's on the active side. And then on the passive side, also you can build passive components in silicon. For example, inductors like microinductors or high density trench capacitors in silicon. So then you can integrate some of the things that normally go on top of the substrate on an FR4 in the substrate, and that increases the power density that you can get out of that power module compared to if you have built the same bill of material on a conventional substrate technology, for example.
So I guess one of the key questions that I'd like to ask is, because that's not an obvious step to go in terms of development when you're thinking about power technology, because usually when we think power technology, we think relatively big things. And I remember talking to Hans, and you're talking about 1,000 amps in some of these components. So what are the key complexities of building power modules based on silicon interposer technology rather than the traditional like FR4 approach? And you had the silicon interposers and then thought, I could use this for power technology and make power modules in that way.
So the thing is, several of the members of the leadership team have industry experience in power related work before. So we come from background, worked for companies, several of the players doing on DC-DC converter technology, and we understand a lot of the limitations that are in that space. That later when we started working on the technology, we could easily see that using that for power converters, for DC-DC converter applications, is one way to really add something like a differentiator on the market here. The research started mainly focusing on the integrated passive devices in silicon, like microinductors and similar. And from there, since you need something like that in a power converter, using that as a substrate for the power converter, it's kind of like how the logical steps went. So starting from integrated passives in silicon to using that as a substrate technology and co-package that with the active circuit or the switching network or so on, and then developing solutions based on that. And in terms of the value proposition of the technology, when you look at, okay, I have this technology, I'm able to drive more watts per millimeter squared out of that, and I'm able to resolve some of the thermal bottlenecks, then there's a number of applications that you can take that to. It's mainly applications in the world of where you have form factor defined components that are increasing or like equipment that are increasing in terms of the functions with every generation. If we look
Hmm.
at consumer devices, if we look at servers, you are increasing the functions and some of the form factor defined applications. And then you want to run more processing power, more functions, and that requires more current, given
Mm.
that the space needs to be very, you have strict limitations
Yeah.
on the real estate that you consume for that. That's one thing. The other thing is in some applications, especially the very high current ones, when we're talking about the 1000 ampere and beyond, in a single load or a single like chip or a module
Mm.
card or so, the issue becomes not just where like the power density, but also the proximity you have to the load. Because even if you have very, very short wires of interconnects driving that like high current to the load, there is a lot of power loss in terms of the I square R losses
Okay.
in
Yeah.
those
Yeah.
interconnects because of the nature of the very high current. It's low voltage, but very high current. And also there is the IR drop that there will be some voltage drop from your load, from your supply to the load, given a very low resistance, but then a lot of current going through that ends up with with some budget for the IR drop. So then it becomes an issue of how can you bring it closer and closer to that
Okay.
load, because every sub-millimeter of interconnect counts. And this is
Yeah.
where it has to do a lot with the packaging technology for these solutions rather than the only the design of the power converter itself.
Okay. So I think that's probably a good place to kind of ask, uh, in terms of what Lotus Microsystems offers at the moment, what components do you have in terms of the power modules?
So we have two products that are currently being rolled on to the market, and one is being in development. One
Okay.
is currently in
Nice.
development, and two of these three are power modules. And in that case, we're talking about a single package that integrates like a PMEC chip together with some of the passive components needed for that power converter, mainly the inductors.
Okay.
And then the third device is what we call a thermal guide. And that's as a simple SMD component that is like a thermal bridge
Okay. Okay.
or thermal jumper as another description. And that's using the thermal capabilities of like the high thermal conductivity of silicon to resolve the hotspots on some of the application components by being able to direct the heat out of a hot area on the PCB
Mm.
to a ground plane that can be then connected to a heatsink or similar. Um, so this is one direction, which is basically through the catalog products that we have,
Hmm.
and then we are working on a number of custom design solution towards a
Oh, nice.
specific
Okay.
application. And in that case, it's kind of like a specific engagement with a custom design, and this is where we look into everything that has to do with the package design and optimizing for a specific use case rather than more of a generic or more of a like a standard component nature of a product.
Okay. So for the ones that you kind of have within the catalog, what kind of applications would you use them in? What kind of uh, power supply are we talking about? If you can describe that.
Yeah, maybe I'll talk about two of them. The first
Okay. Yeah.
one is a power module for um, point of load. Like it can be, we can just generally state it as a general point of load conversion. So it has an input
Hmm.
voltage of up to 5.5 volts, and then an output voltage that is lower than that. So it's like an integrated buck converter. And the number of
Okay. Okay.
applications it can cover include optical modules, some of the telecom applications, FPGA or CPU point of load power
Okay.
conversion, as well as also some medical applications that can leverage such product. And the other one is the thermal guide, and that's a very generic one. We are right now busy creating application notes on different use cases of that. You need that in any application where you have some thermal bottleneck, like a hotspot or a component that is quite hot, and you want to be able to direct some of this heat away and be able to improve the performance of that. the examples are like pin diodes, laser diodes. They normally get quite hot in
Yeah, yeah.
general use, and in power converters and power amplifiers. Some of the applications that get to use that device to improve the performance by being able to reduce the operating temperature of the bill of material.
I guess probably something important to ask, if you have the numbers on top off the top of your head, uh, particularly with the point of load converter. How big are we talking in terms of the component footprint when compared to a typical setup to do the same task?
Yeah, so we can say that we offer up to 30 to 40% reduction of the footprint compared to
That's still a lot, yeah.
like similar like spec for for similar specifications given that power
Hmm.
module, for example. And it can sometimes be not fair just to compare the size, because if you look into
Yeah,
some of the performance of the power converter, you need to look into if there is any derating for the other products, even though they are rated for the same power as as uh, as as per given spec or so. But then when we look into
okay,
the thermal performance across the operational landscape of that, then we'll be able to see that the part is not as performing at some of the loads compared to other nominal loads or so. The same across the temperature, like the ambient temperature of the part, whether you will be able to get the maximum load or continuous current out of the part across the temperature range. So these things make a difference, not just comparing size by size, but then looking into
yeah.
the performance across the operational span is also important.
So you're talking about the thermal bridge. What would people be using at the moment to do the same kind of task, or do they have to just route their traces in a certain way?
So they like right now you will look into how to design the PCB as much as you can to resolve some of these limitations in terms of the thermal performance. In many cases, you will end up with a need for a heatsink to really improve the
Yeah,
performance, one way or another to figure out some thermal ways to get rid of the heat or couple it somehow to a heatsink or similar. That device can help in some cases eliminate the need for that at all, or reduce the investment that you need to do in the requirements for a heatsink or similar in order to take more power out of your device or better performance in general, because it's not always like only power applications we're talking about here. Many circuits perform better if you reduce the temperature. Some end
yeah,
up being more noisy if they are not controlled at the maximum temperature they're running at. There are some reliability concerns on the other side. So it translates to one way or another to some gains that you get that are very relevant to the application, depending on the nature of that application. But yes, the general used to be, if you design this in when you're doing the platform design,
yeah,
then you will be able to reduce some of the investments or the cost associated with either reducing the performance given the heat limitation, or investing in some means for like cooling the application or the circuit using one way or another. Yeah.
I've just realised out of thinking about this is for those thermal bridges, are they electrically and thermally conducted, or are they only thermally conductive and electrically insulating?
Yeah, this is the real. You're spot on. So they are thermally conductive and electrically
Mhm.
insulated. So they will
Ah,
not
okay,
alter
that's
the operation of the circuit by any means. This is why we call it a thermal jumper or so. But thanks for
yeah,
bringing up that point. I think for engineers generally, the way to use this is it's electrically a dummy device. It's a very low capacitance, very high resistance across the pads, but thermally conductive device. So you can just bridge the heat that is a result of some power loss or so from one pad or an area all to another pad, that you can just take it to a ground plane or a thermal plane, and then from there you can connect to a heatsink or similar. So It's just a means to design it in order to improve the thermal performance without any alteration of the electrical performance of the circuit.
That is actually quite a game changer.
And the interesting thing is there are a number of devices on the market that are based on different substrate technologies. What we do is we build it also using the same silicon interposer technology. So it's based on a silicon substrate and some copper termination, the typical way we do also when we use it as a substrate in power converters. But the good thing here is that you can also deliver very, very small sizes of that part, and you can also make them very thin, so they can be embedded in other substrates. And that's a key advantage of that you can, in also PCB embedding technologies, you can use that device to control the thermal performance of the substrate and be able to direct the heat by designing it in the PCB design phase if it needs to be embedded. Otherwise, it's an SMD device that can go on your platform and be able to just resolve some of these thermal bottlenecks that we just described. So
cool.
Using silicon here allows you to have custom sizes of that, very, very small sizes if needed, because basically it's based on a diced wafer. So you can go very small on that, and also very thin compared to what you can get on other substrate technologies.
Very nice. So what's the ideal ending point for this technology, and that's already starting to accomplish stuff that isn't obviously possible at the moment. So where can you see this technology going in, I always like to say 5 years time?
I think our direction is to focus on the power management and thermal management solutions using the substrate, the silicon interposer technology. Or the power silicon interposer technology. So one way is we want to extend the line card of the thermal bridge devices, like the Lotus thermal guide, to cover more sizes, custom solutions for that as well. So sometimes you need also in some high voltage application or so, you need to have some specific dimensions of the part in order to withstand high voltage. And in case you embed it in some solutions, like some substrates, then you need also to control the thickness of that. So to extend the number of standard sizes, like EIA sizes of this, now we're rolling out 04, 02, 06, 03, and 08, 05 sizes, which are quite generic and fits many of the applications requirements that we could see now. And then using that also in our power system in package converters, basically the PCEP technology, in order to design more offerings that cover more applications in this. So right now we are rolling out the LBK0504, which is going to be targeting the general point of load applications, but we'll cover more variants in terms of the load currents and also the input voltage and the output voltage that it can cover, the parts can cover. So this is going with some product like roadmap along these lines for the thermal and power system and package solutions. And then there are the custom solutions. We are already quite active there. And we look forward to be able to help some of the of the customers in like developing some of the most advanced applications to resolve some of the issues with respect to power delivery, to deliver more current in a very confined space with many limitations from the mechanical design of the application itself, and couple that with superior thermal performance that would differentiate our offering compared to doing the same thing on existing packaging solutions.
Do you currently have any evaluation boards for the off-the-shelf models?
Yes, we do, and we encourage everybody to just send us an email. You will find a contact form on the website, as well as like some of the request material for these parts. We'd be happy to send them over for evaluation. and that includes our customers and also engineers and people with interest in this field. We would like to basically offer our solutions for them to test and send us questions or
Cool.
any points of feedback that would be highly valuable. And also within the engineering audience that I hope that we will be talking to or will be seeing this, we're actively hiring as well in Lotus across the
Oh, nice.
domains of integrated circuit design, power electronics engineers, application engineers, process engineers. So please look at the LinkedIn page as well as the website, and feel free to apply for one of our open positions or more. We'll be happy to get people who end up seeing this video to get directed our way and apply.
Cool. Well, thank you so much for this discussion, Ahmed. And I'll admit I've been blown away by some of the explanations, but this is very, very exciting, and I really can't wait to see where this goes next. So, congratulations on making something that I think will change the game.
Thank you very much. I appreciate the time, and quite excited to be featured on your channel, and looking forward to getting any feedback from
Yeah.
people who is going to see this or so. Feel free to reach out to us, and yeah, we're looking forward, and we'll stay in touch.
Hey, yo, where my engineers at?